Today we want to talk about Raman spectroscopy. In 1928, Raman discovers that small changes occur. The frequency of a small portion of light scattered by molecules. The changes reflect the vibrational properties of the molecule. Raman was awarded for this noble discovery in 1930. In 1970s, laser made Raman much more practical. Near-ear lasers allowed for avoidance of fluorescence in many samples. That was a very major drawback for Raman, the occurrence of fluorescence. But near-ear lasers solved the problem. The Raman effect, incident radiation excites virtual states, what you would call distorted or polarized states, that persist for the short time scale of the scattering process. So polarization changes are necessary to form the virtual state, and hence the Raman effect. This you can see in this figure here. We are showing those virtual states, as you can be able to see there. I just have a look at it. So if we can show you there, so this is the, you can see the virtual state. After there is scattering, there is that energy, and then we have HV1 minus HV2, and then now you can see the virtual state, and then you can be able to get the difference, and that difference is characteristic. So Raman spectra are excited by linear polarized radiation, majorly lasers. The scattered radiation is polarized differently depending on the active vibration. Using a polarizer to capture the two components leads to the polarization ratio, as you can see. The polarization ratio P can be used in interpreting the actual vibration responsible for a Raman signal, which is very important. That's the technique. So just the design of dispersive Raman scattering system. So we have a source, radiation source at 90 degrees angle to the sample, and then we have wavelength selector, and then we have detector. So special consideration sources, lasers are generally the only source strong enough to scatter lots of light and lead to detectable Raman scattering. So lasers are provided there that can be used. Then we have, so there you can find many of them that are provided. Then the same problem that infrared has, we also have it, we face it in Raman. Now we need to modulate these signals. So we use the Michelson interferometer, the product of a famous physics experiment. Produces interference patterns from the monochromatic and white lights. So you can be able to see a typical Raman system. You can be able to see common lasers used in Raman spectroscopy plus a few methods of interest in chemistry. So as we have mentioned, the neodymium, yttrium, aluminium, garnet. We have helium, neon. We have argon ion. We have carbon 4 called carbon dioxide. And we have the titanium sapphire. So you can see them versus their wavelengths, as you can be able to see there. Basic applications of Raman spectroscopy. Raman can be used to study aqueous phase samples, and that is very important because this is something that cannot happen in infrared spectroscopy. So AR is normally obscured by water modes or aqueous modes. This happens to be less intense in Raman. However, the water can absorb the scattered Raman light and will damp the spectrum and lower its sensitivity. So actually aqueous solvents or mediums are real problems. Raman has several problems susceptible to fluorescence, so it is very important that you do a thorough. If you want to choose the laser, be very careful. When used to analyze samples at temperatures greater than 250 degrees Celsius, suffers from black body radiation interference. And the same problem is also observed in IR. So when applied to darkly colored samples, the Raman lasers will hit the sample, can cause decomposition and or more black body radiation. That's a very big issue. Advantages of Raman over IR: avoid many interference from solvents, as we have mentioned the aqueous, cells and sample preparation methods, very important. Better selectivity, peaks tend to be narrow, very important, because you see most of the peaks in IR are always broad, like when it tends to functional groups like the strong functional groups like the aqueous, they are always very, very broad. Depolarization studies possible, enhanced effects in some cases. You can detect IR inactive vibrational modes. For example, we've just talked about the vibrational modes in dinitrogen. Advantages of IR over Raman is that Raman can suffer from laser-induced fluorescence and degradation, which is not something they observed in IR. There is nothing like like fluorescence. Raman lines are weaker. The Rayleigh lines is also present. So there is that interference. Raman instruments can be more costly, especially lab systems. Spectra are spread over many micrometers in the IR, but are compressed into several nanometers in the Raman. So that is also an issue. So final conclusion, they are complementary techniques. We cannot say that one is better than the other, because in most cases what Raman does best, IR does not do best. also look at now if they are overlapping. You can check something there. You can see that for Raman, the peaks are not that strong, as you can be able to see. That spectra of the crystal and polymorph of the drug translate. Polymorph of the drug tranilast. Surface enhanced Raman spectroscopy is a form of Raman spectroscopy that involves a molecule adsorbed to the surface of a nanostructured metal surface, which can support local surface plasmon resonance excitations. The Raman scattering intensity depends on the product of the polarizability of the molecules and the intensity of the incident beam. The local surface plasmon resonance amplifies the beam intensity when the beam is in resonance with plasmon energy levels. Then this leads to signal enhancements. In coherent anti-Stokes Raman spectroscopy, the sample is excited by a probe beam with frequency, a Stokes beam, and a probe beam. It uses tightly focused beams delivered via a microscope to achieve a phase matching condition necessary for the coherent process. Raman optical activity is a technique that employs circularly polarized radiations to study chiral molecules. Raman optical activity comes in two flavors: scattered circular polarization and incident circular polarization. Both right angle and backscattered configurations are used. Main applications are to chiral analysis and molecules conformation. So that's the end of our study. We can do further studies, the Scooge and Holler. We also have other books, very important books, like the Raman effect by D.A. Long. We have Lesser Physics, like published by Hess Hooker. We have Atkins also has done a lot of work on molecular quantum mechanics, which you can be able to study. Thank you. Subscribe.